My screen. All right, thank you. So as James was saying, my name is Mihai. I'm at Laloyaux of Bonn. Thank you for having me speak today. My topic is AI-DOP, which is a machine learning path from Earth system observations directly to a global medium range forecast. And I'm presenting on behalf of a big team, the Laloyaux, which includes Tobias Necker, who's, I think, joining us today. Just to set some context, some taxonomy, if you wish, I'm going to describe two parallel but also complementary forecast streams being developed at Laloyaux. The first one being the physics slash the hybrid stream, which involves the acquiring observations, running the 4D bars, so producing an analysis and initial condition for the forecast model, and then running one of the operational forecast models at Laloyaux for the medium range, which are the IFS, the integrated forecast system, and the AIFS, the machine learned version, the machine learned forecast system that has been operational at Laloyaux for more than a year, I think. And as you can see from the figure, we have a hard dependency on 4D bars. So the forecast model cannot start before the analysis is actually available. Option 2 would be having a pure machine learned forecast stream. So, and which includes an implicit or an explicit data simulation step. This would also be observation-based, so ingesting observations, feeding them into an end-to-end data-driven machine learning system, which directly produces a forecast, and perhaps also an observation-based reanalysis for R&D. Basically, the Laloyaux objective on the medium term is to build one of a robust and operations-ready data-driven end-to-end system. What specifically that system is going to look like is still a research problem. So AI-DOP is one of the possibilities, but we also have research incoming from AIFS to be complemented with observation information from projects such as the Weather Gen and other things going on at the center. Why would we want to learn from observations? Well, the long and short of it is that observation-driven AI models, unlike, let's say, the majority of the machine learning models developed thus far, have the potential to reduce both initial condition and model errors, whereas reanalysis-driven AI models such as AIFS, GraphCast, and others have seen era 5, are started from the analysis in initial conditions, have perhaps been fine-tuned on operational analysis developed at the weather centers, and can only learn to reduce model errors. So they cannot address the shortcomings of the initial conditions, and there's lots of value to unlock in reducing initial condition errors. Just one slide about the AI-DOP concept. It's an end-to-end system. So we go from observations, as I've said, straight to a medium range forecast. We use both satellite observations and in situ data. They're ingested in one or more input windows, and then we forecast observations in subsequent windows. So it's observations to observations. There's no reanalysis data being used. There's no signal coming in from the likes of ERA 5, ERA 6, or the operational analysis from Laloyaux. It's completely independent of those. But the basic idea, the basic kind of like requirement in this scenario is that the network learns a representation of the physical state and the physical processes that the observations are sensitive to, because otherwise it cannot build a reasonable or a physical state of the, knowledge about the physical state of the atmosphere. So just a diagram to walk you through what's going on. So we have information observation space, satellite and in situ data, and we project this onto a latent space using a learn DA function. So this DA function, between quotes, combines information from different observation sources into a unified latent state, which is that yellow circle. And then we have a learned forecast model, which evolves the latent state forward in time, and then learned observation operators, which map back information from the latent space back into observation space to produce an observation space forecast. It's the encoder processor decoder paradigm that other models such as AIFS and GraphCast have been using to great success. Right. So a word about the training data. We have, so this slide hides a huge amount of work done by some of my colleagues at ECN-OLF. So data QC, data curation. So we have taken a huge amount of observations from the archives and from the operational streams at ECN-OLF to create machine learning friendly data sets in the ZAR format. This includes, as I've said, satellite sources, conventional sources, and also data that has not been assimilated in IFS, such as precipitation observations from the likes of GPM, so the GPM satellite. QC is still crucial, so some of these data have been bias corrected and QC'd. Yes, this is quite an important step to take before you can do machine learning on observations. And you can see the data coverage of various satellites is quite inhomogeneous. You have instruments coming and going. So that's also something to keep in mind when designing an observation-based model. A word about the structure of GraphDOP. So the architecture that I'm going to go quickly through. Again, it's based on the encoder, processor, decoder paradigm, and you have observations coming in inside one or more windows of observations. In this case, I'm just showing a single window for simplicity with the link, basically a 12-hour window. So you have observations coming in, they're encoded onto the latent space using a graph neural net. Then the processor, which is also a learnable module, a neural net, evolves the latent space using perhaps time stepping. So in this case, you have 3 hours sub-stepping in the latent space. And after each sub-step, you have the decoding step, which projects information from the latent space back onto the observation space. So it's kind of like the complementary operation of the encoding, that is the decoding. And then optionally, you can have a regressive rollout, so you can pass information, forecast information back to the input and continue the forecasting process. So this allows you to produce a medium range forecast in 12-hour windows at one time. Yes, so does this work? So first evidence that it does do something sensible. So again, this is trying to forecast all the observations in the target window. There are 2 locations. We know where the observations are gonna be. For some satellites, we know the weather stations are, and so on. So we can forecast during training. We can have the model forecast at those locations, and we know what the actual truth is gonna be like. This shows a 5-day forecast of Sidiri. I think the animation, yes. And you can see very nice cloud features. You can see signs of so representations of convection and extratropical dynamics, specifically in the southern hemisphere and also in the north. And again, all of this is from observations alone. So the model learns to represent these from having seen Sidiri data and other observations as well outside of the Sidiri disk. Moreover, we can make predictions on a regular grid. So the thing is, we train on the actual locations of we train the model on the actual locations of the observations, but at inference time, we can decode. We can use the decoders to decode, that is, forecast any of the observed quantities at arbitrary locations and times inside the target window. So we just need to know the locations and the time relative to the end of the window, and then we can ask, okay, decode the wind observations or a wind observation over the South Pacific, where there's no wind observations, actual wind observations available during training. So you get you get a very nice gridded forecast, and you can see, for example, for the South Pacific, you get features in the wind forecast that are not seen in the input observations. So there's no direct wind observations over those areas. So it means that GraphTop has learned a model of the correlation or relationship between different observables. So especially satellite data that that constrains the wind forecast in this case. Yes, and these are 200 hectopascal winds, so jets. We can have GraphCast make predictions for any observed variable, so not just winds or geopotential, anything that we can observe basically. So this includes significant wave height, SST, precip accumulation, infrared radiances, microwaves, visible, anything in the visible spectrum. As long as we have observations of this, then we can ask the model to forecast them. I included some use cases to show you what GraphTop can do, and I'm also going to include a link at the end to a presentation from a colleague of mine, Eulalie Boucher, from last week, and I think she shows other examples of what GraphTop can do with the latent state. So watch that if you have some time. But in this case, this experiment shows that GraphTop can infer features that are not directly present in the input observation. So this is a case where we have a Severi only as input, so 12 channels of the Severi Meteosat geostationary satellite, and we have the observation, the conventional observation, so wind, geopotential, temperature, and so on from synops and buoys and whatnot as targets, and Severi as well as a target. So we don't use conventional observations as input, so the model just gets information of those through the loss function. But you can see there's quite good agreement between the GraphTop prediction from this experiment and the ECMWF operational analysis. You can see there's agreement in the MSLP contours, the locations of the low, and also T850, so the shaded contours, and then the wind barbs representing the jets. Yes, and the point is that the second point is that in this experiment, the predictions revert towards a climatological state as soon as we go outside of the input information domain. So you have a big reduction in the RMSE for the winds and MSLP inside the Severi disk, which is highlighted in yellow. Outside the model reverts towards essentially the climatological state using just the signal that comes in through the loss term. But another very nice thing that I haven't had time to show here is that if you add more observations, more observation types, CRIS, GNSSRO, and so on, and as well, if you extend the input window, so we've done ablation experiments of this, you get incremental skill improvement. So the model is able to learn complementary information from all of these and produce a better forecast each time. So there's not more information fed to the model means a better forecast at the end. Right, so the latest scores that we have, I think Eulalie also showed these last week. At the surface, we're doing quite well. So again, this is against IFS. So this IFS has not been post-processed, so keep that in mind. We should probably get some small improvements in IFS for post-processing, so this is good to keep in mind. But we have very good skill for surface parameters, and that's arguably because the near surface conditions are being constrained well by the information available in the observations. For the upper air, we're trailing IFS, except for the very short range, and I think So we're looking into ways to basically improve the autoregressive rollout to keep the error accumulations low. So I think so we've seen that for at least as of now, the errors are accumulating faster in GraphTop than they do in IFS. So this is something that we're investigating now. Right, and I'll spend the rest of my presentation on more of a data simulation-like topic, just to stay in the theme of this workshop. Specifically, how to use classic, let's say, data simulation tools to study the physical consistency of DOP. So using adjoint gradients, we can that we get quote unquote for free from a machine learning model. It's possible to have the model produce a forecast for a given location, in this case, the Kerguelen Islands in the southern Indian Ocean, and then interrogate the model to ask it basically which input observations have the highest contribution to that forecast, or let's say to an error in that forecast using this adjoint framework. So in this case, we're asking this of a T2M 12-hour forecast over the Kerguelen Islands, and we're looking at the sensitivity of T2M synops and ATMS channel 1. Yes, and you can see there's some implicit localization, and this is because of the inductive bias of the model. So basically, this is because of how attention on the processor and the locality in the graph mappers is also the model is able to put the spatial limit on the information that's pulled to produce a forecast at a certain point, which is a good thing. Again, we can also, using the adjoints, you can trace back information upstream. In this case, for a storm in Ireland, we say we want to see which observations in ATMS channel 20. This is a humidity channel, which gives us the information about mid-latitude storms. So which observations affect or influence a forecast of surface pressure over Ireland on the 8th of November 2022, and there was a storm hitting that region. So you can see that information extends upstream, so to the west as you go backwards in time. Again, this is very sensible and what you'd expect to see also in a physics-based model. We can use diagnostics such as FSOI, so the forecast sensitivity-based observation impact, to estimate how every observation contributes to reducing the forecast error. And this is work being done with Patrick, Laloyaux, and also Tobias here at ECNOLF. And just looking at the simple experiment with just a few satellites, you can see that the good news is that 95% of the channels used to train the DOP model contribute towards reducing the forecast error after 12 hours. And we can see that for ATMS channel 1, we have the largest impact over the ocean. ATMS channel 22, the humidity channel, has the largest impact for observations at the end of the input window. And again, this is consistent with what people have seen for physics-based models. More recent observations towards the end of the window have higher importance. And I'm going to finish by just showing the last slide, the prototype near real-time observation-based system that's been running at ECNOLF for maybe a couple of months now. Which basically acquires, processes, and archives observations as they come into the center. It makes them into ZARs for easy machine learning applications, and then runs inference with a pre-trained model and archives the forecasted observations. There's a bunch of research questions that I won't go through, but a lot of important things need to happen before such a system is made robust to say errors in the observations or drops in the observations. And my very last slide has an example forecast, but I'll just mention that forecasts are delivered 10 minutes after observation cutoff, so that's quite fast, and there's still room for improvement if we reduce the cost of I/O, which is the bulk of the cost of producing a forecast. Yes, and this is one example forecast, and you can see that it's broadly consistent with the IFS signal, again operational DCNWF and the IFS control, and all of them verifiable against the analysis and observations. Right, thank you.
Great, thank you very much, Mihai. Great talk. So let's go straight to the questions because we have a few on the OPAD. So Swanpan Malik, he asks, Chris, the cross-track infrared sounder has over 1,000 infrared channels. What criteria are used to select a specific channel or profiler in AI-DOP?
Right. So we have in-house experts on Chris, and basically we have used their advice to narrow to basically reduce the channel count to 60 odd channels, essentially the most important channels that are also candidates for a simulation in IFS. So broadly, we have, and this not only applies to Chris, but for the other satellites as well, we've taken broadly the channels that are being assimilated in the IFS, in the physics-based model, for use in DOP. Yeah.
Okay, great. Maybe another quick question from Anthony Weaver. Observation quality control typically involves checks against a model background. What do you do in AI-DOP?
Right. So this is something that we've just begun to explore now. So we have a few ideas on how to do observation QC independent of a physics-based model, perhaps using a recent DOP forecast as the background. But we have other ideas as well. For training, the quality control is partly based on first guess departure. So we still have this weak dependency to the 4D bar system, but we have ideas on how to remove that dependency as well. Perhaps use a climatology that has been generated by AI-DOP itself, for example. Yeah, but it's still research work at this point. Yep.
Okay, great. Thank you very much. We do have another question, but I think in the time reasons we need to move on. So thank you very much, Mihai. Maybe you can answer the question in the OPAD.